Right, let's get started. Test 2 done. All right, we're starting Task 3 content. Holy crap, it goes fast. Task 3 content. Means the Task 1 expected deadline. Hopefully y'all hit that. Haven't looked at the stats yet. Had a busy weekend, haven't had a chance to do it. But the Task 1, if you did not finish that, don't forget we have the 3 deadlines. I don't feel like going over what that all implies, but especially when we get to the first final deadline, I think I'll start mentioning that a little bit more in lecture, but I might not because anyone who that affects probably doesn't show up to lecture with high, statistically speaking, most of them probably don't, but anyway. Make sure, if you didn't finish Task 1 yet, make sure you're definitely keeping an eye on the final deadline and the late deadline if you still want to snag an AO. Okay, but linked lists. Let's start talking about Task 3 stuff. And this is why the final deadline. We're already talking about linked lists. If you're still working on the basics of unit testing, you're just too far behind. Not right now, don't get me wrong. But at that final deadline for Task 1, if we get to that and you're still working on Task 1 and we're talking about, we're on to the next testing strategies, we're done with linked lists, and you're still working on week 1, Task 1, when we're about to start inheritance, you're just too far behind to get caught up at that point. Start planning for a future semester at that point. Okay, linked lists. Let's do this. I realize I got to adjust my timing for memory diagrams using the tool. My timing is just so far off with these things. We're going to keep on track today. So array lists, before we talk about linked lists, we need something, I guess we don't need, but let's get something to compare it to. Array list or just arrays or lists in Python. I might have misspoke there. I always forget the underlying data structure for lists in Python. It might actually be linked lists. I don't know. Anyway, array lists and arrays, I definitely know how these work off the top of my head. The way they work is one continuous block of memory with random access to all of its values. That means if you have the memory address for the first element of an array, you can easily compute the exact memory address of any element in that array. And this first memory address of an array, that is the memory address that's stored in memory in a variable of type array list. In Java, that's obfuscated quite a bit. When you get to 220 in C, that will be very direct. You will actually have the memory address, and you can do this math yourself to access a new memory address and then access the value at that memory address. Java hides all the details on us, or for us, depending on your view. But this math is still happening under the hood. This is fixed size. Since all of the memory is one continuous block for an array, we cannot resize an array because if we're trying to add an element to the end, that memory address that we need a very specific place in memory, and that memory address might already be used by another program or another variable in our program, another value in our program. So we cannot change the size. It's just not how arrays work. Array lists let us pretend we can change the size, but as we saw, array list is a wrapper class for an array. It does use an array under the hood, and that underlying array cannot change size. When an array list wants to change its size, it will change the size of that array. It will create a brand new array of a new size and delete the old one, copy all the values over. Not in that order. And this is kind of what it looks like in memory. We'll have a reference to the first element in the array list, the beginning of the array list, the memory address of the first byte. And I haven't talked too much about memory addresses. I just said OX and then some random number and kind of left it at that. But this is one of the few times in 116 where I'll go into this in a little bit more detail. The memory address is an actual index of memory. So the memory address, our RAM, I want to be on the next slide when I talk about this. Our RAM is one giant array, effectively. It's an array of bytes, and a memory address is effectively an index on that array. And then that array can store all kinds of values, of course, which are the bytes for our information. So if we have an array list of ints, in Java being 32-bit values, if we have an array list of 32, or an array, I should just say array for this slide, array of 32-bit ints, and the first memory address is OX200. I say 200, but it's 200 in hex, but 200. Then to compute the memory address of any value at any index in this array, we're going to use a little bit of math. The index times 4, a 32-bit integer, is 4 bytes. And when memory address, memory stores bytes, just bits in groups of 8. And you run this number, this math, index times 4, the size of one element in bytes, plus the memory address of the start of the, oh, actually my slide is broken. The memory address of the first element. So if the index is 0, then 0 times 4 plus the starting memory address, we just get OX200. And that's why our indices start at 0. It makes this math work out great. Index 0 is just the memory address of the array itself. That's the only value we actually store in our variables for that array. And if we want index 2, 2 times 4 plus 200 gives us 208. And that's the memory address of this element, so we can access that directly. We go to memory and we say, give me the value at memory address OX208, and we go directly to that value with no extra steps, just a multiplication and an addition, and then we go directly to that place in memory. My slides are actually broken. This 12, I'm pretending that this is decimal. This should be 20C. 20C, that value should be. I used this slide for a while, and I just realized I made that mistake, since these are hex values. And this is why we call memory RAM, random access memory, because it has this random access property. Random access, you can access any value by doing this one multiplication, one addition. That's random access. Our arrays are random access. And our memory is effectively one giant array of bytes indexed by memory addresses. So that's how we get random access memory, RAM. It's memory, it's bytes, that's random access. You have that mixed up with hash maps. And you have that. Array list will keep track of the order of the elements. Hash maps will not. But there is a predefined order in hash maps. It's just something that we're not concerned about in 1.16. When you talk about hash tables in CSE 250, you'll go through all the underlying how that works. Hash maps actually are built with arrays, for what it's worth, but there's a lot that goes into it, exactly how to build those arrays. You take I'll do a very brief one. I haven't got to talk about hash tables in a while, and it kind of came up naturally. You take a hash of the key, and that hash gives you the index in the array where you should store that value. Actually, that was easy. Got one sentence. There's hash tables for you. Hash maps are built on hash tables, so that's effectively how hash maps work. It's an array, but the index where the value is stored is a hash of the key, and the hash of the key, depending on the hash function, gives us something that's effectively random to us humans, but it is deterministic, so it will always be the same value for the same input. But that's why we get the values in a mixed up order, because some key might map to index 32 in your array, or another one might map to 2, and it just gets all kind of shuffled up based on that hash function. I'm not going to go far down that tangent. Okay. Any other questions about arrays? I just want to remind us how, we went a little further than we did before too, but reminder of how array lists work so we can compare it to linked lists, because why the hell would we even introduce linked lists if they don't do something that arrays can't? Or else we would just use array lists for everything, like a lot of developers do, to be honest. Just use array lists for everything. So linked lists is another sequential data structure, so it does care about the order of the elements. Just like array list, it would keep track of the order in which we insert these elements. We can sort an array list. It doesn't make sense to sort a hash map when it doesn't care about order to begin with. we can sort a linked list. The order will be preserved. It will be meaningful. So we call it a sequential data structure. And where the differences start, the big difference, is that it's spread across memory. A linked list is not one continuous block of memory. So we don't have the same effects that our arrays have. So a few things here. One, we get variable size. This is a wonderful property. If we want to add a new element to an array list, we'll go anywhere in memory. We'll ask our operating system and say, hey, I want a new value added to my linked list. We get a location of heap space anywhere, and we say, cool, I'll take it. I'll take whatever space you give me. And then we're going to link that to the rest of the list by taking the memory address of the new value that we added, the new memory address we have, and tell the previous value in the list where to find the next value. So each value in a linked list knows where in memory to find the next value in the list. And in this way, our list elements are linked together by knowing where to find that next one in memory. It could be anywhere in memory. It's not a continuous block anymore. So we no longer have random access, but we can change the size of the list by putting the new value anywhere and then telling the rest of the list, hey, here's where you can find that value. So we do this with objects. That's why we have to do objects before we talk about linked lists. Objects and references, we learned these last week. We have to have a firm understanding of these to understand how linked lists work. So each link in the list, which I'm going to start calling nodes, each node in the linked list knows two separate values, and it will be an object. So we create these nodes as objects. Each object is going to know the value at that part of the list and where to find the next node. So it'll have the value it's storing and the next node as a reference. It'll have a reference to the next object that stores the next value and a reference to the next node. And that next node will store its value and a reference to the next node. The next node will store its value and a reference to the next node, so on and so forth, until one of the nodes references to the next node is this special keyword null. This means there is no next node. I'm the end of the list, and that's how we know when to stop looking at the list. We call this null terminated, and we'll see this when we're looking at the code. This will be a little more clear. But we call this null terminated. When we reach null, we know we've reached the end of the list. So in our code, we're going to see a lot of if node equals null, if next equals null. We're going to see that stuff to check, are we at the end of the list? If we're at the end of the list, do one thing. If we're not at the end of the list, do another thing. Null terminated. This is something you'll see a lot more of in 220. So we want to give you a taste of it with linked lists in 116. In 220, even your strings are going to be null terminated. There's no such thing as a string when you're coding in C. It's a null terminated array of characters. So getting used to it now, getting used to this concept will benefit you when you start really using it extensively in C. And here's the code. Here's a linked list with a main method for an example. So the code itself, the class defining objects of this type, not much to it. We're going to add some more helper methods to this. We're going to add to this class as we go through the week. But this is all we need. We have two instance variables, the value that this node stores, and a reference to the next value or the next node in the list. That's all we need. And then a constructor that takes those two values as parameters and sets them equal to the instance, or sets the instance variables equal to those values. So it's a class that just stores these two values, the value at this portion of the list and a reference to the next node in the list. It's a linked list, and through these references, that's how we're linking nodes together, and that's why we come up with linked lists. It's a whole bunch of links that are, I lost the analogy there. It's a whole bunch of nodes that are linked together to form a full list. And then just like an array list, or rather an array, was a reference to the first element in the array, and then we did math on the reference to find all the rest of the elements in the array. A linked list is a reference to the first node of the list, which we call the head node, the head of the list. And that's all we store in memory. If we have a variable that we think of as storing a linked list, it's actually only storing a reference to the first node of that list. When I just store the next address in a linked list is the difference between the current and next memory hex address to save space. Because we don't know anything about those memory addresses. It's up to how the operating system gives us memory, or the JVM in our case of Java. And they can be anywhere. Make sure I understand the question. The difference between the current and next to save space. Current is like memory address 1, and next is memory address, max memory address -2. It's still going to be the same amount of space, if I'm understanding the question. Because there's no guarantee that these nodes will be anywhere remotely even close to each other in memory. So we can't make any assumptions on the actual values of those addresses. What happens if you skip a value in the input of the constructor? Depends what you mean by skip. If you consider, here I'm giving it null, if you consider that skipping, that's our expected use case for linked lists. We're going to start seeing null quite often in our code, starting with today. If you legit skip it, if I say new linked list node of 1, close paren, that's going to be a compilation error. The code's not going to run. Okay, and then to create a linked list, I'm going to create a linked list variable, store a reference to a new object of type linked list node. I'm giving value of 1 and next of null. So when I first create this linked list, it's a linked list of size 1 with just the value 1. Next is null, so there is no second node to this list. And then this line usually trips students up the first time you see this one. It makes more sense when we get to the memory diagram, in my opinion. But this line is pretty trippy. We're taking a variable, reassigning it to a constructor call, a new object, that takes the variable itself as one of its arguments. This gets trippy because the first is on the left and right-hand side of the assignment operator. But we're creating a new... the key to understanding this line is we resolve the right-hand side of the equal sign of the assignment operator first. So we're going to look at the right-hand side. When we resolve this constructor, it's 2, and then whatever first resolves to, which is a reference to this object, and then return a reference to the new object and replace the value of first with a reference to the new node that was created. And then we do that again. So at the end, first is going to be a reference to this linked list node of the value 3. Its next is going to be a reference to this node with value 2. Its next is going to be a reference to this node with value 1. And its next will be null, signifying that it is the end of the list. So we end up with a list with the values 3, 2, 1, and it looks a little more like this when we visualize it. So the variable first stores a reference to the node with value 3, which stores a reference to the node with value 2, which stores a reference to the node with value 1, and its next is null, saying it's the end of the list. And each of these nodes can be anywhere in heap space, anywhere in memory. Any memory address the operating system decided to cough up when we asked for space, that's where these things are. We don't know where they are. We don't care where they are. And to add a new node, we create a new node anywhere in memory and then link it to the rest of the list via references. So each time when we created a node, we create this node, we get it anywhere in memory, we put the value 3 there, and then next is a reference to the old head of the list. And we can add to the end of the list. We create a new node here and set this next equal to a reference to that node. We can add nodes with high flexibility in a linked list, unlike what we could do with arrays, where we can't change the size at all. We can change the size of a linked list. We can insert nodes to the middle of the list if we wanted to, just by updating the references and being careful about how we update those references. So very flexible in that sense. What happens if you skip a value in the input? Oh, I already read that. For example, the int input to 5 and not 2 after inputting 5 and not 2. Like if this 2 was a 5, I think that's what you're saying, everything would work perfectly fine. I just chose 1, 2, 3 because I wasn't creative when I created this slide. Those ints can be whatever we want them to be. If I want to insert 562, negative 43, and then 0, the code here would work exactly the same. Just the lists that I create will have different values in them. The code will still function exactly the same. I think that's what you're getting at there. There's nothing special about 1, 2, 3. Those don't have to be in order. Nothing about them is meaningful in this example. Just the first 3 numbers I thought of, and I thought of the first 3 numbers, except I started at 1 instead of 0, so I should be punished for that one. The first time we call the linked list class, it's always null. Hesitant to go with always, but in this case, yeah, I think so. For all our use cases, the first time you have no list at all and you want to create the first node, this next is going to be null because you have a list of size 1. The only, it's not really an exception. I don't want to get too technical on my answer. I will a little bit. If you, instead of null right here, you could replace this null with new linked list node of int of 2 and then null, but at least one of them has to be null, have null as its next, even if you create the whole list in one single line. And I'd argue that the first one that's resolved is the one that has null as an argument, so it would still be the first one would be null, even if I want to get technical about it. Is there a primary reason why I would use linked list over other data structures? Because you can easily change its size. The ultimate answer to that question is performance. There's certain use cases where you're going to want a linked list because it's going to perform much better. It's going to be faster than an array list. Most of that conversation I'll save for CSE 250. They'll tell you all about how to choose the right data structure for the right problem. But that will end up being the ultimate answer. Or else we'd use array list for everything. If we don't care about performance, array list for everything is going to do everything you want it to. Not literally everything, but that's why we have hash maps as well. But you wouldn't ever use a linked list if you didn't care about performance. But if you can afford to have an array list where every once in a while it has to create a brand new array, copy all these values, so if you can take that performance hit at, not literally random, but at seemingly random times, then and that overall increase to your runtime doesn't really matter. And a few other operations, say you want to remove the very first element of an array list. Actually, let me give a full example of this. The answer is performance, but let me give an example of why. I have an array list. It's got 1 million elements in it, or let's say 1 billion. 1 million's a pretty small number to a computer these days. But I have an array list with 1 billion elements in it, and I want to remove the first one, the one in the value at index 0. I want to remove from this array list or array. Well, array is even worse because you got to create a whole new array. But I want to remove the first element from an array list of 1 billion elements. What do I have to do that? One, I remove the element. Okay, element's gone. But now I have nothing at index 0. So what I have to do is go to the rest of the 999,999,999 elements and move all of them down one spot in memory. So I have to do what we call O of n operations, for where n is the number of elements in the data structure, to be able to remove that first element from the array list. Or else I have an empty index 0. I can't have that. So everything's copied. And that's how an array list does it. It'll copy everything and move everything down by one value. Very expensive operation. A linked list, I want to remove the element 3. Even if there's 1 billion elements after this, I say first equals first.next. I'm done. That's it. So we call an O of 1 operation, constant time. Doesn't matter how big the list is. All I had to do was manipulate one reference in one node, and that's it. I'm done. I didn't even actually change the list. I just changed the reference store. Where's the list? That's it. I'm done. So certain operations, and then certain operations are faster with array lists. I picked one because I want a solid So I want to sell you on linked lists today. I picked one where linked list performs a lot better. But there's a lot of trade-offs like that. So depending on your actual application, if you have large amounts of data, choosing the right data structure can significantly impact the performance of your code. Okay, that was too much of a tangent. Let's go. I'm going to mostly skip this memory diagram. I'm going to do a second one that encompasses all of this one, and then I'll do it in the tracing tool when we get to memory diagrams. But this is what it's going to look like in memory. I'll talk about the last one a little bit. First, got a reference to the first node that was created. And then when we created the second one, first was OX350. So next was OX350, next is OX350. This returned OX200, so OX350 was replaced with OX200, which has a reference to OX350. And then same thing here, we created OX480 that got a next of 200, and then replaced first with the 480. So first is just a reference to 480, which has a reference to 200, which has a reference to 350, which has a reference of null. And I have my list 3, 2, 1, end. You notice the memory addresses. I chose random memory addresses for these. They can be all over memory. They don't have to be sequential. They don't have to be increasing, decreasing. There's no pattern that they have to follow. These things are anywhere in memory, and we don't care where they are. We just care that they're somewhere in memory, and that we have a memory address that we can use as a reference to link these nodes together. Okay, let's talk about toString. We briefly talked about toString before. The least efficient data structure is even harder. Yeah. As an extra challenge, what's the worst data structure you can choose for each application? And first in, last out, and first in, last out, first in, first out. The stack and queue, we're going to talk about both of those on Friday. And those are two applications that are basically built for linked lists. Like linked list is the answer of how to build those two data structures. Building either one of those with an array list would be awful and slow. Okay, toString we talked about briefly. I don't really want to talk about toString itself, but we are overriding a toString. I did not talk about override annotations at all, did I? I think I don't bring that up until next week, officially in the slides. But we're overriding the toString method here to override the default behavior of printing out basically garbage. And we're going to use some recursion for this. And the note here, I don't know who left this, but absolutely true. Recursion's the best. Recursion's so much fun. I'll be honest too, recursion isn't always the most useful thing, but I think it's fun, so I do like it. It's not always like the right answer or the best answer, but sometimes it is. And we will get to cases where it is, and we'll have many cases where it isn't, but I'm going to use it even when I don't have to or shouldn't to give you more practice with recursion, so you get recursion. With recursion, I'll do my whole recursion speech right now. With recursion, you're not going to feel the benefits of it through linked lists. I will use it all this week. We're going to use lots of recursion to give you practice with it and exposure to it. But a loop would suffice for any of these linked list algorithms. Where recursion is really going to pay off is when we get to trees in 3 weeks. 4 weeks because of break, right? I don't remember. But in 3 weeks of content, when we get to trees, writing the tree algorithms without recursion is exceedingly difficult. And if you're trying to write those recursive algorithms on trees without practice with recursion, which a lot of students do, I don't even get mad anymore. I just give you this warning. If you don't get practice with recursion this week when I'm recommending it, when you get to trees and it's effectively required, you can do trees without recursion. It's just tons and tons and tons more work. If you get into that without any practice with recursion, you're going to have a hard time working around recursion with trees, because if the first recursive methods you write are with trees, those are those can get trickier to write. These ones are going to be pretty simple. This is about the simplest recursive method you can get right here. aside from the addition one we did earlier. Actually, this one might even be easier. You don't want the tree ones to be the first recursive methods you ever write. So don't put yourself in that position. Get the practice now. When you're working on task 3, I would use recursion for your methods there to find the average of a linked list of ratings is the first method you have to write. Testing, actually comparing 2 linked lists too. Using recursion there to get some practice. I strongly recommend it. Because then, bless you, because then you'll be all practiced up when you do need it. Because trees, academic or not, real world or not, trees just beg for recursion. It just makes things so much easier to work with if you know recursion when you get to trees. Anyway, that's my thing. We're at the next memory diagram, so let's head over to the tracing tool. Let's do this. Okay. Try to do this not slow as crap like I did last time. We're going to get to the end of this one. So we start with our main method, as always. We have new stack frame main. We're creating a variable first with no value. We create it just so we have a return arrow for our new stack frame, which is a linked list. Oh, crap. This code isn't the same as what I showed on the slides. I'm going to change it quick. I'll call this a foreshadow. On Wednesday, we're going to add these type parameters. But I don't want to mix that with the introduction to linked list. I got them all. Okay, now it's what we saw in the slides. Okay, so this is a linked list node int. Every non-static method, the first thing we put in the stack frame is the keyword this. We don't have a value for it quite yet because we don't have an object. We're going to get an object of type linked list node int. IO until the very end. Link the parent. A linked list node has value and next as its instance variables. So as soon as we create the object, we slap the instance variables in there. And then the stack frame, we got 002, OX02. And the constructor takes val and next. Remember, the instance variables is not always a one-to-one correlation with the parameters. It's close this time, except we have val instead of value in one spot. So noting that difference is, admittedly very minor in this case. But when one of the parameters is completely absent, if it just took val and didn't take next, make sure you don't put next in your stack frame. We talked about this last time, but worth reminding, especially since you had the first graded quiz this week. Don't put extra variables in your code block, in your stack frame if they're not constructor parameters. And next is null. I haven't really talked about what null is, so let's talk about that now. Null means the lack of a reference. So what null means is this variable is supposed to store a reference to an object, and it doesn't. So it's the lack of a reference. You can't store, since it's the lack of a reference, you can't store null in, say, a variable of type int, of a primitive type, because primitives don't store references anyway. They store values. So a primitive can't store null, but any object, bless you, any variable of an object type can store null, which means I'm supposed to refer to an object, but I don't. If you try to access anything from a null, so if I say next.null or next.whatever, try to do anything with it. As soon as you say dot, the dot operator means this is a reference, take me to your object. If you use the dot operator on a variable that stores null, you're going to get what's called a null pointer exception, which means you tried to follow a null reference, but a null reference doesn't refer to any object. What object do you want it to take you to? And it's just going to crash your program. It just blows up. So when we have null, when we're working with null, we always want to check, is this thing null? Because if it's null, I don't want to use it at all. I'm just going to treat it as nothing. But if it's not null, now I can safely use the dot operator and head over to its object. On task 3, right from the first testing utility, when you're comparing two linked lists, make sure you're not following a null reference. It's going to be a little tricky when you can't even see the linked lists. Specifically when the linked lists, I'm going a little too far on this tangent, but when the linked lists are two different sizes, don't assume anything about the size. Always check and assert, is this thing not null? Because if it's null, I don't want to get a null pointer exception when I submit to Autolab. So make sure you're looking out for that. Okay, with that tangent, done. This dot value equals val. This dot value equals val. That's how we got the values over there. This thing's done. Cross it out. OXO2 constructor resolves to a reference to the object that was created. And then I have a new linked list that I'm creating, and I'm going to use the clone stack frame feature to try to save a little bit of work here. Uncross this. Move the return arrow. Oh, actually it does return to the same thing, so I could have left that. This. Value is 2. Next, in this line, this is the line that gets tricky. I said it'd be more clear on the memory diagram, and I hope I'm right. I hope it's clear here. Is when we put this constructor on the stack frame, we resolve the right-hand side of the assignment first because we need to know what to assign this variable to. So we put this on the stack frame. 2 is just 2, easy enough. And then first, we're going to look at our memory diagram. First has the value OX002. So OX002. Oh, and I didn't update. I deleted this, right? Maybe I space it. Yeah, there we go. Then I want a new object. Can I clone this thing too? No. Bless you. Put that in my clipboard. Cool. Value. Let me just fill these in. This is where I lose a lot of time on the memory diagrams when it's repetitive. Usually I would just have all this populate in one slide and say, it's the same thing as before. OX002. And we got OX003. This returns. Cross out, new value, OX003. And then we do it again. So I'm going to clone this to save some time. Return arrow's fine. Create a new object. This is still in my clipboard. Value 3, new variable. Next. And next for this one, it's going to get the value of first, which is OX003. So next is OX003. This, OX04, value is 3. At value 3, next is OX003. And when this returns, it's going to return OX04, this OX04. That's the creation of our linked lists. We have first with a reference of OX04, which has a value 3, and next of OX03 with a value 2, next of OX02 with a value 1, and a next of null. So we effectively have the list 3, 2, 1 stored in memory at the variable first. Any questions on the creation of our linked list? Yes, for task 3, use the linked list node class in the data structures folder in ratings. And I give that in the assignment, so then for grading, Autolab, and your testing, and your code, we're all using the same exact class and the same exact package. Because I used to say, create a data structures package and copy linked list node from the course notes. And I used to say that, and then one little typo, it's data structure instead of data structures, and it's just a pain in the ass for the student. So I just put it in the handout this time. Just make sure you use that handout linked list. Why do I like recursion so much? Is there some theory you did a dissertation on that involves it? No, I don't know. It's just, I just find it interesting on like a kind of nerdy level. It's, what recursion does is leverages the structure of the program's stack to keep track of information for you. And I just always thought that was pretty neat, that we're taking advantage of just the way programs execute in memory and then using that as part of our algorithms themselves. It's just kind of nutty in a fun way. Plus the proofs, when you get to proving recursive algorithms, the proofs kind of write themselves too. It's always a proof by induction where it just follows the structure of your recursion. Yes. Oh, good point. This is a little more thoughtful on garbage collection. Nowhere on the stack, like these three constructors are no longer in memory. They're crossed out. That means they don't exist anymore. So in memory, we only have OX004 as a reference in memory. But OX002 and OX003 will not be garbage collected. They will not be garbage collected because we can still access them, although indirectly. We can't access them directly from the stack, but we can go 04 to 03 to 02. We still can access references to them, so they will not be garbage collected. Okay, but we're going to finish this thing today. So we have first .toString. We're going to call our toString method toString, and it's first .toString. First, which results to OX004 .toString. We're calling toString from this object right here. So this, every non-static method has this as the first thing in its stack frame. OX004, the calling object. This is a reference to the calling object. This object at OX004 is the object that called the method. So this is the object referred to by the keyword this. And we're going to run the code. toString doesn't take any parameters, so all I have in this thing is this. I'm going to create out as an empty string. Out plus equals this dot value. So cross this out. This dot value is 3. So this is 3. Oh, I wish I should have updated the code. Paul wrote this code, so I'm blaming him. He's creating an empty string so he can get away with this string concatenation. If you say string out equals this dot value, it'll be a type error because you're assigning an int to a string. But he's taking advantage of string concatenation. If you have a string and concatenate it with an int, Java will convert the int to a string for you. So that's why we have 2 lines to do this one thing. You could do string out equals string dot value of this dot value. I guess that's kind of gross too. So maybe this is the best way to do it. But or string dot out equals empty string plus this dot value. Maybe that'd be my preferred way to do it. Just combine it into one line. But anyway, not that big of a deal. We'll live. And then if this dot next equals null, this dot next equals null is false. So this, or sorry, not equals null is true. This does not equal null, so it's true. So we go into the conditional. There are no variables being declared inside this code block, so I'm not going to worry about my dashed box for my code block because it'll be empty, not going to be concerned with it. But we do make a recursive call here. This dot next dot toString is calling the same method. So let's get our stack frame. This is where we got to really keep track of things. This, and this is going to be a test if you've been following these references, the dot operator. This, what the keyword this does, is this. When this line is executed, we're in this stack frame right here, and we have this. Dot means follow the reference. Next, which resolves to OX003. Dot, which means follow the reference, again, takes us to this object, and then dot toString. So at this object, we're calling toString. So in our new stack frame, our reference this is going to be OX003 because that's the object where we ended up when we called that method. So in the new stack frame, this OX03. So following what the reference this is, we're really abusing that in the toString method here. So following that is very important. Then out, empty string, cross out plus equals this dot value. So out equals this dot value 2. Then the next recursive call. So we have another toString. Conditional is going to be true. And what is this? Okay, this from this stack frame here, this dot next dot toString, we're calling it from this object right here, OX02. OX02, variable out, empty string, cross it out, 1, this dot value is 1. If this dot next not equal null is now false, so we're going to return out. So we're crossing this thing out. Oops. I need my return arrows here. I'm used to my recursion not returning. It's not really an assignment. Oh, I don't know what the quiz team would want here. I would return it to out, even though it's not a strict assignment. The concatenation. Oh, I didn't even create my variable here.